This section introduces what a graph is and what working with one costs you. A graph inverts the usual data posture. It foregrounds the relations between points and demotes the point's own properties. Nodes and edges, nothing more. Yet, the formalism is general enough to carry social ties, molecules, interactomes, and road networks all at once. The chapter's real payload is what that inversion costs downstream. Ordinary machine learning rests on data points being independent and identically distributed. Graph data breaks this at the root, because a node is its connections, so you cannot model it in isolation. Every task the book will chase, labeling nodes, predicting missing edges, classifying whole graphs, is therefore a bet that structure is signal. This bet has a name, homophily. Neighbors tend to resemble each other. The whole book reduces to a single instruction. Learn from the relations, and let the structure itself be the thing you learn from. This section explains the single inversion that makes a graph fracture standard machine learning. A graph makes the relationship the object of study, demoting the individual data point to something secondary, and that one inversion is what breaks the ordinary machinery. Every conventional model assumes its data points are independent and identically distributed. A graph is precisely a declaration that they are not. ODs borrow their labels from their neighbors, a property called homophily, so dependency becomes the signal rather than noise to be modeled away. The chapter lists a taxonomy of tasks: node classification, relation prediction, community detection, and whole graph prediction. That taxonomy is secondary scaffolding. What it exists to establish is that once you learn over connections, the partition between supervised and unsupervised learning dissolves, and no standard category fits cleanly. Every later chapter is a way to encode that non-independence. The book opens by removing the assumption the rest of machine learning rests on. This section explains the shared skeleton behind every traditional approach in the chapter. Each technique is one move wearing different masks. A human hand designs a fixed function from graph structure to a feature vector, then hands that vector to an off-the-shelf classifier that never touches the graph itself. The named methods are all instances of that one move: degree, eigenvector, and betweenness, centrality, the clustering coefficient, motif counts over a node's ecograph, neighborhood overlap heuristics, and spectral partitions of the Laplacian. Each is just one such hand-built encoder, differing only in which structural signal it privileges. Learning happens downstream only in which structural signal it privileges. Learning happens downstream. Motif count ecograph. This is the before that the book exists to negate. The chapter names the extract, then classifies skeleton precisely so that later chapters can make its extractor differentiable. Hold that skeleton. Every deep architecture ahead is the same skeleton, with the hand design dissolved into gradient. This section explains why every method in Chapter 2 shares one hidden constraint, and what dissolving that constraint buys you. Before anything is learned, a human supplies the invariant. Every method the chapter tours is one hand. Chosen function from graph to fixed feature vector. Degree and the centralities. Weisweiler. Lyman graph kernels. Neighborhood. Overlap scores. Spectral clustering of the graph. Laplacian. Each one is picked by hand, not learned. The chapter orders these methods by task: classify nodes, predict links, cluster communities. That ordering betrays the constraint. No shared representation exists yet, so each task earns its own bespoke heuristic. This is the foil. The rest of the book dissolves. Learn the feature map. and the 3 task-specific toolkits collapse into one. Read the chapter as the manual baseline against which representation learning is measured. Note that the Laplacian is the one construction that survives into the learned era. This section explains the single move behind every shallow node embedding method in the chapter. Every one of these methods is one move wearing different masks. You encode each node to a vector. You decode a pairwise score from 2 vectors, and you tune the vectors so that the score reproduces some chosen node similarity, which we call S. The encoder is trivial, just a lookup table, so all the content lives in what you decide, neighborhood overlap memes. That single choice is what partitions the zoo. Factorization methods pick a deterministic S, a power of the adjacency matrix, and solve it by SVD. Random walk methods pick a stochastic S co-occurrence on short walks. Line stitches together first-order and second-order adjacency. 3 families, 1 skeleton. The reconstruction target is the only real degree of freedom. This section explains why every shallow node embedding method is really one point in a 3-coordinate design space. Fix the coordinates and the method regenerates itself. The framing comes from Chapter 3, Encode, then Decode. The encoder is a trivial lookup, one learned vector per node, so it carries no structure of its own. The entire zoo, Laplacian eigenmaps, Gray Reap, Hope, Deep Walk, and Node 2Veek differs only in 3 choices. The first choice is the decoder, which reconstructs a pairwise relation from 2 embeddings. The second is the similarity target it must match. The third is the loss that scores the gap between them. Read the chapter's summary table as exactly those 3 columns, and each row derives itself. The telos here is negative. This baseline's contentless encoder is precisely what the graph neural networks of Part 2 exist to replace. This section explains what changes when a graph edge carries a label. Chapter 3, Embedded a node as a point. Here, the edge carries a label, so a pair of points no longer fixes a fact on its own. The move is to fold the relation into the decoder itself. You score the triple U, tau, V, by letting an operator R tau mediate between the 2 node embeddings, then you train it to reconstruct the adjacency tensor. The decoder regenerates the fact that U treats V rather than storing it. The whole chapter is one question rotated across decoders. The geometry you grant that operator fixes which logical patterns it can express. Translation buys only anti-symmetry. A symmetric dot product buys only symmetry. A rotation in the complex plane buys both, plus inversion and composition. Expressive power is the operator's algebra, never its dimension. This section explains why a knowledge graph is a tensor rather than a matrix, and what that one fact fixes about every embedding method built on it. A knowledge graph is a tensor, where a matrix has 2 axes, the graph has a third because every edge carries a relation type. So scoring becomes a 3-argument problem. The decoder takes the embedding of the source node, ZU, the relation type tau, and the embedding of the target node, ZV, instead of just 2 node embeddings. That single move, promoting the decoder from pairwise to relation parameterized, is the whole chapter. Everything after it is one design axis, what algebra the relation slot imposes. The candidates line up by their multiplication. Rescal makes the relation a full matrix. Trans-E makes it a translation. Distmult makes it a diagonal. Complex makes it a conjugate. Rotate E makes it a rotation. The generative primitive is this. An embedding method is its decoder, and the decoder's algebra fixes exactly which logical patterns it can represent: symmetry, anti-symmetry, inversion, and composition. You predict a method's power by reading its multiplication, not its loss. This section explains why a graph neural network has the shape it does. A graph carries no canonical node ordering, so any honest function over it must ignore that ordering. Permutation equivariance is the symmetry the data demands. Flattening an adjacency matrix into a multi-layer perceptron violates that symmetry. The architecture has to be generated by the constraint instead. The only move that respects an unordered neighborhood is to aggregate over it as a set, then fold the result back into the node and iterate. Do this k times, and each node's embedding has absorbed its k-hop neighborhood, structure, and features alike. That is the whole graph, neural network, neural message passing, equivariant by construction, because the aggregate step eats a set. The symmetry is not a property you check afterward. It is what forces the design. This section explains why a graph neural network has the shape it does. A graph carries no canonical ordering of its nodes, so any honest function on it must return the same answer under relabeling. That property is permutation invariance, or equivariance, when the output is per node. That single constraint generates the entire architecture. The only order-blind thing you can do with a node's neighbors is aggregate them as a set, then update the node's own vector with the result. Iterate this k times, and each embedding absorbs its k-hop neighborhood, structure, and features at once. The chapter's move is symmetry dictates form. The graph neural network is derived, the minimal, deep encoder. The graph's own symmetry permits, replacing part 1's shallow, per-node lookup with one that actually reads the neighborhood. This section explains what changes and what stays fixed once a graph neural network is put to work. The whole chapter reduces to one move. An architecture emits embeddings, and everything downstream is just choosing what to regress them against. Chapter 5. Build the machines that turn a graph into vectors, one vector z sub u for each node and one vector z sub g for the graph as a whole. Here the machine is held fixed, and the three canonical tasks, node classification, graph classification, and relation prediction, collapse onto three losses laid over those same vectors. Softmax, squared error, and relation prediction collapse onto three losses laid over those same vectors. The surprise that does the work rides on that pattern. Pre-training a graph neural network to reconstruct neighborhoods buys nothing because message passing already smears neighbors together, so the objective is redundant with the mechanism. Practice is loss selection over a frozen embedding producer. This section explains how a graph neural network gets its task and where that task actually lives. A graph neural network's architecture is task agnostic. What the network is for enters entirely through the loss bolted onto its output embeddings. Chapter 5 built the message passing machine. This chapter's thesis is that the same node embedding ZU and the same graph embedding ZU and the same graph embedding ZG feed any of three interchangeable heads, a softmax over nodes, a squared error over pooled graphs, a pairwise score over node pairs. The chapter's sharp surprise sits underneath. You cannot usefully pre-train a graph neural network by reconstructing neighborhoods, because message passing already is neighborhood reconstruction. The objective is redundant with the mechanism. Everything else, practical, sparse, matrix, multiply efficiency, neighbor subsampling, edge dropout, is engineering to make that neutral machine run and generalize. This section explains why graph neural networks are best understood as one object reached by three independent derivations that happen to meet. Graph neural networks were reached from three separate places: from graph signal processing, where convolution is generalized off the Euclidean grid onto a graph spectrum, from message passing for probabilistic inference in graphical models, and from the Weisweiler-Lehmann isomorphism test. Three lineages that never coordinated, all converging on the same aggregate and update kernel. The move that makes this matter is to read the artifact by its invariances, not by its birth story. A construction that admits three motivations, none of them derivable from the others, is characterized by what it does. Each motivation is a different chart on that one manifold. The structural payoff is this: the lens you adopt bends what you build next. So the convergence is not trivia. It is a menu of orthogonal intuitions you may recombine at will. This section explains how graph neural networks arrive at a single object and why three separate approaches reaching it is the whole argument. Three fields walk toward graph neural networks from unrelated starting points and arrived at the same door. Spectral graph signal processing came first, generalizing the Fourier transform off the grid. Message passing came second, borrowed from probabilistic inference on graphical models. The Weisweiler and Lehmann isomorphism test came third, bounding what such a network can tell apart. The chapter's move is that this triple convergence is itself the argument. An object reachable independently from convolution, from inference, and from combinatorics belongs to no single field. It is a fixed point of the graph domain. Which motivation you adopt shapes which extensions look natural. The same object, read three ways, seeds three research programs. This framing is deferred until after the model, because motivation reads cleaner in retrospect. This section explains the 8 traditional approaches to graph generation and the single design choice that all of them share. You generate a graph by hand, writing the rule for one number, the probability that an edge exists between two nodes. That single design choice is the whole primitive. Realism is engineered in by hand, one property per model, rather than learned from data. The 3 canonical models form a ladder, each one patching what the last ignores. Erdős Rényi fixes only density. Every edge is equally likely. The stochastic block model adds community by making that probability depend on which block each node sits in. Preferential attachment adds heavy-tailed degrees by growing the graph autoregressively, so new nodes attachment adds heavy-tailed degrees by growing the graph autoregressively, so new nodes attach in proportion to existing deg. You'll predict the next model by asking which real-world property the current one still flattens. This layer explains what graph generation is at its root. Generation is embedding. Run backwards. The embedding chapters took a graph and produced a vector. Here, the arrow reverses. A handful of parameters produces a graph. That inversion is the whole primitive. Traditional graph generation makes it concrete by hand, specifying one thing: the edge likelihood, the probability that a given pair of nodes U and V share an edge. Everything else is a ladder of realism bought against tractability. Erdős Rényi fixes a single density R and captures almost nothing. The stochastic block model spends more parameters to buy community structure. Preferential attachment goes autoregressive, growing the graph so that degree begets degree to buy heavy-tailed hubs. Each rung adds exactly one real-world property. This is the pre-deep learning backdrop that the learned generators of Chapter 9 are built to overthrow. This section explains the one choice that organizes the whole chapter on deep generative models for graphs. Hand-coded graph generators fix the process. The move is to learn it instead. The chapter's entire design space collapses to a single choice: how you factor the joint distribution over edges. One path is to sample every edge independently in one shot, a learned echo of the previous chapter's ER and SBM models. This gives you variational autoencoders and generative adversarial networks, cheap but blind to clustering, since independence cannot manufacture correlation. The other path is to generate edges sequentially, each one conditioned on those already placed. This is the autoregressive move, a learned preferential attachment. Now dependence, and therefore motifs and grids, becomes expressible. Variational autoencoders, generative adversarial networks, and autoregressive models are the same three general, deep generative recipes ported to graphs. A graph's realizable richness is exactly the conditional structure that its factorization admits. This section explains the single move that turns a hand-written graph generator into a learned one. The previous chapter hand wrote the rule that manufactures graphs: plant community structure, plant a degree distribution, sample. This chapter's single move is to delete the rule and keep only examples. You hand the model a set of graphs, G1 through Gn, together with a reconstruction objective, and you let it fit the generating distribution itself. This is the same shift as going from a coded simulation to a learned one, from writing the program to inferring it. Everything downstream lives on one axis. Either you generate the whole adjacency matrix all at once, which is the learned echo of Erdős-Rényi and the stochastic block model, or you grow the graph incrementally, each edge conditioned on the prior edges, which is the learned echo of preferential attachment. There are three vessels: the variational autoencoder, the generative adversarial network, and the autoregressive model, but one primitive underneath them all. Replace the handcrafted process with a fitted one.